Before we can begin making games, we need to kind of understand how objects are represented in our game worlds and how they relate to each other. Now, video games use either a 2D or a 3D coordinate system that's based off of a Cartesian coordinate system. Basically what that means is that we are going to pick some point as our origin, and everything else is going to be in relation to that point. All screen items are represented by a series of lines and points, and what we're going to see in 3D game development is everything is a series of triangles. All objects, circles, squares, rectangles, everything can be made up of many small triangles. These lines and points are located on a coordinate system. So whether we're working with 2D or whether we're working with 3D, we are going to be working with actual points in space. A coordinate system has a series of perpendicular lines. Each line is called an axis, and every system has an origin. The origin is where all the axes meet. Alright, so if I'm in a 2D system, I have an X and a Y axis, and the point in which they intersect each other is going to be called the origin, which is the basis of all the directions. All points can be represented by their distance from the origin. What we have here is we have a sample coordinate system. And you can see in this coordinate system that it is a two-dimensional coordinate system. We have our X and our Y axis. The X extends from the left to the right, and the Y extends from the bottom to the top. If I were to move leftward from the origin, I would be moving into the negative territory. If I were to move right from the origin, I'd be moving into the positive territory. Likewise, if I were to move up from the origin, I'd be moving in the positive Y territory. If I were to move down from the origin, I would be moving in the negative Y direction. We can look at a few sample points here. We have our origin, which is labeled as 0, 0. It's not in any direction from itself. It's right on top of itself. Now, if I were to move 2 spaces to the right and 2 spaces up from the origin, I would be in the positive 2, comma, positive 2. The first 2 representing the x-axis and the second 2 representing the y-axis. Another point we have is at negative 3, comma 3. By seeing that, I know that it is 3 units to the left of the origin and 3 units above the origin. If that were to be moved below, it would be a negative number, and a second negative number tells me that it's to the left of the origin and below the origin as well. Now, visual games are based on one of 2 systems. A game can be either 2D, standing for two-dimensional, and will use a horizontal and vertical axis, or an X and a Y. A game can also be a 3D system, standing for 3 dimensions, and those games are based on 3 axes, the horizontal, vertical, and depth axes, which is referred to as the X for horizontal, Y for vertical, and Z for depth. In Unity, we will be working primarily with a 3D coordinate system. Now, the thing to know about 3D is we're all familiar with X and Y, left, right, up, down, but Z is directly towards the player. So if I move along the Z axis, I will be either moving away from the player or towards the player, and that's what gives us our 3 dimensions. Here we have a side-by-side comparison of the 2 systems. On the left, we have a 2-dimensional coordinate system. So we can see the representation of a square in 2 dimensions. Everything is flat in this system. There is no distance from the player. On the right, we have a sample 3D coordinate system. Again, we have a square, or in this case, since it's 3D, we call it a cube. The cube has all 4 points that make up the front face, like in a 2D system, but since we have this third axis, this depth, we can actually make a square out of 6 sides, and the sides can represent the distances from the player. Now, when making our game, we have a couple different types of internal coordinate systems. These are most often used in 3D coordinate systems, but we can talk about them in 2D coordinate systems as well. So what we have is we have the world coordinate system and we have the local coordinate system. The world coordinate system is shared by all objects in the world, and it has only a single origin. So every object in the world will refer to the same origin when talking about its location. The local system is unique to each object, and each object will have its own origin. In this image, we have 2 sample 2D coordinate systems. The one on the left is using the world coordinate system. What we can see is the square represented here has drawn all 4 of its points relative to the one world origin. So we can see the lower left-hand point is 3, 2, signifying that it's 3 units to the right of the origin and 2 units above the origin. The upper right corner of the square, however, is 9, 8, meaning that it's 9 units to the right of the origin and 8 units above the origin. The other image here on the right hand side is a local coordinate system. We can see that relative to this square, our origin is in the middle of this square. As a result, the lower left-hand corner is at -3, -3, meaning that it is 3 units to the left and 3 units below its local origin. And the upper right-hand position is 3, 3, meaning that it is 3 units to the right and 3 units above the local origin. It's imperative to note that in a local coordinate system, every object has its own origin. So any other objects in this scene would be drawn relative to themselves, not to each other, and not to some shared global origin. Most games utilize some form of motion. A video game where the items on the screen didn't move at all may not be the most exciting video game. When we move and manipulate our objects in a 3D coordinate system, it's called transformations. We use these transformations to change object position, size, and so on and so forth. So the first transformation I want to talk about is translation. Translation involves moving our objects along one or more axes. So if I were to move it to the left, I could say that I translated it in the negative x-axis. If I moved it up, I translated it in the positive y-axis. I can translate objects along more than one axis at a time, but translation is basically moving its position along these axes. The second transformation we have is rotation. Rotation is when we spin our object about one or more of the axes. If I were to say spin a square from left to right, I would be rotating it about the z-axis, the z-axis being the axis that's coming from the viewer straight into the object. However, if it were to spin like a top, then we would say we are rotating it about the y-axis, the y coming from up and down and piercing it through the middle that way. So when we rotate something, we identify what axis is moving through that object in that direction, and we rotate it about that axis. We can get more complex rotations by rotating it about multiple axes at the same time to kind of get maybe a diagonal spin. Finally, I want to talk about scaling. Scaling is the transformation where we expand or decrease the size of our object about one or more axes. So if I wanted to make my square wider, I might expand it about the x-axis. If I wanted to make it taller, I'd scale it about the y-axis. If I wanted to make it deeper, I would scale it about the z-axis. So I can modify the size of my objects in multiple directions by scaling it along multiple axes at the same time. Here we see an image of a sample translation. We're basically going to move an item from one location to another. So we have on the screen here an image of a square being moved from the left to the right. It's a very simple transformation to apply. Next, we have a sample rotation. Now, a rotation can be a little bit more complicated, and we can see here on the screen an example of a square being rotated about the z-axis. I know it's being rotated about the z-axis because if I were to push a pin through the object from me to the object and then attempt to spin it, that's the direction it would spin. So I know I'm spinning it about the z-axis. Finally, scaling. This image here is being scaled along the x and y axis to make it smaller in both its width and its height. Now, it is a 2D image, so we can't really tell if it's being scaled along the z-axis, but in a 3D environment, we would be able to see these things. Alright, so before we rush off and we just start transforming all of our objects all over the place, the order in which transformations are called on an object is very important in the process of moving things around. Certain transformations modify the local coordinate system of our objects and thus will change how the transformations are applied. For example, if we were to rotate and then translate our object, it will be in a different spot than if we translated first and rotated after that. Transformations, like I said, are based off the local coordinate system. Therefore, one transformation will affect the other transformations that come after it. In this image here, we can see precisely what I mean by that. So in the image on the left, we see that we are going to translate a box from the left to the right, and then we're going to rotate it about the z-axis. And in this case, I can say I'm rotating it in a negative direction about the z-axis, and we're rotating from the right to the left. Now, in the image on the right, we can see that we rotate about the z-axis first, and then we translate the object. So you can see how the object ends up in a different location than if we had done that in reverse order, if we had translated and then rotated. So we can see that the order of transformation is very important for determining how an object is going to look and how an object is going to be positioned. If I were to, say, scale an object and then move it, it would move much further because the scale would be much larger. Likewise, if I were to scale it much smaller and then move it, it would move less distance because the local coordinate system would be a smaller scale. So basically, while you're working with your objects, just pay attention to how we're manipulating them and pay attention to the order in which we do things, and you'll be okay.